Hello, everyone. My name is Alejandro Dominguez from the University of Illinois, and I would like to welcome you today to PSERC's webinar. Thank you for joining us. The speaker today is my colleague Richard Zhang, and he'll be talking about power system state estimation. This is joint work with one of his PhD students, Ivan Guzel. So, Richard, whenever you are ready, go for it.
All right, thank you very much for the introduction, Alejandro. Very happy to be here today to talk about state estimation. I would like to begin by talking about our growing excitement about AI for grid applications. So there's a lot of excitement, there's also a lot of hesitation. It's understandable. As humans, we've always been skeptical of these machines. And in fact, take chess as an example. In 1989, Garry Kasparov, then the world champion, famously dismissed the idea that machines could ever surpass human players. He argued that computers lack intuition, imagination, creativity, the very qualities that made chess a human endeavor. And even in 1997, when he was famously defeated, he refused to concede that the machine was intelligent. He compared it to a programmable alarm clock, something capable of brute force calculations, but nothing more. And at the time, many believed that chess was really at the ceiling, the limit of machine intelligence. Deep Blue succeeded because it could exhaustively try every possible move, but a game like Go, with an exponentially larger decision space, was seen as an insurmountable challenge. And yet we know that 2 decades later, that assumption was shattered when AlphaGo managed to defeat Lee Sedol. And in spite of all these challenges, there's continued to be skepticism because there's this question of whether this AI can really be practically useful. Chess, shogi, Go, these sorts of games that they managed to be in the 2016, these are structured games. They have clear rules. They have a finite number of possibilities and defined objectives. And real world, half the challenge is trying to figure out what the rules are in the first place. To navigate the infinite possibilities and to make decisions in unstructured environments. And that skepticism began to melt, I would say, with the release of ChatGPT in 2022. And suddenly we see that AI was able to engage in open-ended reasoning, generate human-like responses beyond just pattern matching. And the development of AlphaFold really revolutionized the development of drugs and the discovery of drugs. And before, an entire PhD would be dedicated to solving a single protein folding problem. And with AI now, more than 200 million protein structures have been identified. And for this achievement, this is why this particular group was then awarded the Nobel Prize in 2024 in chemistry. So now with all these achievements in mind, it forced us to reconsider what is possible and to really ask, what can AI possibly do for the electric grid? And I mean, electric grid over the past century has been mostly operated based on experience, intuition, a deep technical knowledge of what's going on. And the operators see the same patterns repeat and they learn from their past failures, develop an instinct for when and how to intervene. And yet our grid today is evolving into something that is new, right? With the rise of electric vehicles, the large-scale integration of renewables, the increasing decentralization of power generation is reshaping the way that electricity is produced, distributed, and consumed. Variability is replacing predictability, and the old rules, they don't apply anymore. And this novel setting, one where nobody really has any intuition, one can ask, can we use AI to bridge the gap, to supplant or complement human intuition? But it's important to point out that the electric grid is not chess. It's not protein folding. And this is a point that us grid people have to constantly make to AI researchers. And there's a fundamental difference in that there's a physical reality behind every decision we make. So in other applications of AI, mistakes can be undone and trial and error is inconsequential. But on the grid, one bad decision can have humongous real-world consequences, equipment failures, blackouts, cascading failures, etc. Right? And because of that, there's always been this need for feedback to understand what's actually going on with human operators and with our hope of one day having some AI there. It's always this need for a perception layer that turns this continuous stream of real-time signals, ones and zeros, into meaningful parameters that can be understood semantically by the problem solver, be it human or algorithm. And we really need these algorithms that can perform sensing estimation and to infer what's going on to extract meaningful insights. And maybe one day AI could surpass us in the actual solution part of operating the electric grid, but us humans by far and away have this innate ability to perceive, to interpret, to understand complex systems. And this ability to perceive is something that we've only started to work on in the context of machines. And so instead of talking about chess and protein folding, probably a better analogy is to self-driving cars. And we see this classic example in which perception is essentially the entire problem. Here we see this video from Google Waymo in which you see this cars driving around San Francisco, and it's trying to avoid, in this case now, an oncoming vehicle, and the car is somehow detecting that a vehicle is there and making decisions to drive around the vehicle. And we see the important thing is not the driving part, that's relatively easy, but it's actually being able to detect a pedestrian crossing the road, understand that the pedestrian wants to cross, and then to make the very simple decision of stopping the car. But the perception part is really the hard problem, which for us humans is very easy. It's for us very easy to notice a bicycle coming into our path, but this is the crowning challenge for self-driving cars. And I believe this is also the crowning challenge for broadly cyber physical systems, such as electric grids. And in the context of self-driving cars, we can really see that when you get things wrong, that's when the bad news really happens, right? So we've seen accidents, we've seen fatalities when self-driving cars just do not see a bicyclist and end up with serious incidences. And moreover, the machine perception is very fragile. And so when you feed pictures of stop signs in which you strategically place graffiti onto the stop sign, you're able to trick the perception layer into believing that it's seeing a 45-mile-per-hour speed limit rather than a stop sign. And you can imagine the sorts of incorrect decisions that an automated system would make. Very, very scary. Moreover, these sorts of graffiti type attacks, these sort of adversarial examples, they're even more broad than just simple pictures and manipulating signs. In fact, we can print out three-dimensional objects that will fool, in this case here, Google's perception image recognition into thinking that this 3D printed turtle is a rifle with 85% confidence. And we can imagine that this in the real world would be a very bad thing, to trust the algorithm to make decisions. I would once again argue it's really that perception layer that is really at fault. So there's a lot of work to be done before we can really say that we can develop the same level of perception for electric grid that has already come a long way for other applications of AI. And I think so far, much of what we've done is to apply relatively standard off-the-shelf techniques like linear approximations, KKT, MILB, SDP. And these achieve results, but because they're general purpose techniques, they naturally lie on a Pareto frontier, or in which the best you can achieve is whatever the best you can achieve. And so the approach that my group takes in this work is to ask, what is it about the electric grid that fundamentally makes it different from other problems like self-driving cars, airline scheduling? What makes the electric grid fundamentally different? And then we ask whether this structure can be used to provably improve the cost of an algorithm, the performance, the efficiency, the reliability, the robustness, and the safety of the algorithm. And we'll see today an example in which we establish a fundamental connection between the grid perception problem and a problem that appears in nonlinear physics as well as a mathematical non-convex optimization, something called phase synchronization. So this is an outline of my talk. I will begin by reviewing the perception problem on the electric grid. I want to focus in on this specific problem called state estimation. I want to explain what it is and explain why you have to get this right and how you typically go about solving this problem. And then I want to review what phase synchronization means exactly. And this part will be a little bit more technical, in which I'll actually go in and talk about how this problem is solved elsewhere using a technique based on eigenvectors. And we'll see that by transporting some of these ideas to the electric grid, we gain two benefits. That one, we get a mathematically provably good estimation of the grid, and two is that we get a certificate that our estimation is in fact a correct estimation on the grid. And finally, I just want to wrap up this talk by talking about some of the potential future directions in consequence to some of the stuff that we have developed. And all the work that I describe here can be found in this paper. The QR code is shown on the screen. Okay, so the electric grid is this very large object. It's very, very complicated. It has thousands of nodes and thousands of lines. And here I'm showing a map of the high voltage grid in my surrounding area. University of Illinois, Urbana-Champaign is in fact here in Champaign, which is about, in fact, 2 hours drive from Chicago. I would just see this very small grid is really incredibly complicated. We have lines of different voltages, and we have many, many different load centers throughout. So let's just simplify this conversation by considering a model in which we just have a single generator and a single load. And the generator here is, in fact, we have, in reality, 3 nuclear power plants somewhere outside of Chicago, and we just consider this simplified problem of generating power to power a single city, that is the city of Champaign. And we think about what this problem entail from a decision-making standpoint. There's lots of stuff going on. Most importantly, there's sinusoidal voltage at both the generation and the load. And when you're operating the system, what you want to know is you do not really want to see the voltage waveforms. Rather, you want to know 3 pieces of information. One, you want to know what the amplitude of the generation voltage is, and you want to know what the amplitude of this load voltage. Most importantly, you want to know the phase difference between the generation and the load, the phase difference in the sinusoids. And if I know these 3 pieces of information, I can make all kinds of predictions about the underlying system. I essentially understand the system in some rigorous sense. As a basic example, I can make a prediction on the amount of power that's flowing from the generator to the load. And the underlying system parameters, I have ways of estimating it. So knowing these state variables we call V1, V2, and delta 1, 2 would allow us to make all kinds of predictions. And this is why then, at least at the transmission level, most of these voltages will be measured directly, and it's very easy to directly measure them with the use of voltage transformers. We step these voltages down, we can see the sinusoids, and we can just directly measure the amplitudes. But the angular difference, that phase difference, turns out to be particularly difficult to measure. And if you think about it, it makes sense, because our generation is 100 miles away from the load. It takes 2 hours to drive between the generator and the load. And you can imagine even the speed of light is not really fast enough for us to just naively measure this phase difference. Nowadays, we have PMUs, they synchronize to GPS, but by and large, it's very difficult to measure this phase difference here. So indeed, what we do most of the time in the grid is we measure the power flow across from the generator to the load, and actually work backwards to figure out what the angular difference is, what the phase difference is. So that is something that we're trying to estimate, and trying to estimate this quantity is essentially the essence of the state estimation problem. If we can estimate these states, then we understand the system. Now, I want to talk about the angles specifically. Why do we need to know the angles? Why is it such an important thing for us to solve? So to understand that, we really need to understand the electric grid as essentially rotating masses. We have a massive rotating body at the generator, at the nuclear power plant, that is rotating at 60 hertz, 60 rotations per second. And out here at our load, we have the grid, which is in some sense another rotating body that also rotates at 60 rotations per second. And that transmission line in between is something like a rod, something like a transmission rod that in our case is 100 miles long. And it is really that slight twisting of the rod that causes power to be transferred. And so if we think about if there is no twisting in the rod, then there will be no power transfer. And as we slightly increase the load, that very, very long rod will experience a very, very slight twisting. And in doing so, carrying that load. And as we increase that load, that twisting increases. And at some point, that twisting reaches a maximum value. In the case of electricity from the physics, we in fact understand that this limit is 90 degrees. And once we exceed this limit, then the synchronization is lost, and the physical analogy would be that the rod snaps. So we'll get a blackout on the load. We in fact have a loss of load on the generation side, which can also be catastrophic and lead to nuclear meltdown from the generation side. So this is very scary. And what we want to know is not just, are we going to lose synchronization? Is this rod going to snap? We're much more interested in this question of how close are we to the rod hitting its fundamental limit. And this is something that you can imagine is very hard to directly measure. You have a rod that goes 100 miles long, and it's only a twist of 90 degrees across this 100 miles. And we need to know this value in order for us to understand, can the system withstand a perturbation, a loss of another line, or a loss of another generator, or would this cause the rod to snap and cause a cascading failure in the grid? And I also want to address this question, which I hear a lot from the mathematical community, the AI community, which is kind of like, well, is this really even a problem? You're measuring the power flow. You know this B parameter here, the susceptance, and you measure the voltage directly, the voltage magnitude directly. So can't you just solve for delta? Why is this even a problem? So to answer this question, it's important to point out that our measurements are not perfect. They're slightly noisy. They can be very noisy, and the compounding of the noise is what causes this problem to be non-trivial. So here, so far, what we talked about is just a single generator and a single load, and we have a single line in between them, and we can measure the power flow across this line, and we can make an estimation that, let's just say, is up to 5% accurate in the difference in the angles. But then if we add another line, then there's another 5% error. If we add another line, and we think about how many lines there were at the start of the segment here, right, with all of the different loads and generators in the electric grid, and these errors will continue to compound until you reach perhaps a loop in the grid, and you see that this creates an inconsistency in which you're making a measurement and the cumulative errors add up to such that they do not align, and you have very, very large mistakes as you keep increasing out the spanning the grid. So these small mistakes eventually add up, and we need some way of making estimation that will jointly account for all of these measurements, rather than selectively accounting for some of them and allowing accumulation of errors to appear. And here we also see that it only takes a very small number of bad measurements to completely destroy the accuracy of our estimation. If even just one of these measurements was more imprecise, let's say it has a 10 to 20% error, then it's going to dramatically increase the error of the resulting estimation, and that is not good enough. So we want to see the angles exactly. It's like taking the eyes off the road. It's not good to not know what the values are. So we can see how this problem is actually solved in practice is they solve an estimation problem. Yeah, they solve, instead of having equality between all the power and the B, the VA, VB, they then solve this optimization to make the equations fit as much as possible. And in reality, they measure other powers, not just the power flow between the lines, but maybe the power injection into nodes, the reactive power injection into nodes, and formulating all of this, we end up with a loss function which we're trying to optimize over the angles of each of the buses. And this is a non-convex optimization problem, and that means that we get this complicated landscape in which we need to start off with an initial guess, and we'll progressively refine that initial guess. We can refine that using a variety of algorithms. In power, the usual standard is to use the Gauss-Newton method. There has been attempts to use other algorithms like gradient descent, etc. But long story short, these are iterative refinement that locally improve until they converge to hopefully the global minimum in which that corresponds to the maximum likelihood estimation that somehow solves for the least amount of inconsistencies between all the measurements and somehow is the best guess for what is actually going on. So in the context of non-convection optimization, we have severe issues just from the get-go. And all of us who have worked on this problem know that it's quite easy to induce the algorithm to not converge. And this could be from just an initial guess that's a little bit further away. It could be from bad measurements. It could be from inaccuracies in the system topology. And when it fails, we know that it fails. We can see that it fails, but it's still not good. It's like for a moment taking our eyes off the road. But this is something that we know for sure happens. That when it happens, we can detect that it happens. What's even more problematic in the context of non-convex optimization that has not really come to light until the past, I would say, 5 or 6 years, is this idea that maybe we could converge, but we could converge to an incorrect estimate altogether. And that's to say, we could converge to a different estimation that says the system is in danger when in fact the system is perfectly safe and we're perfectly okay. And that might induce us to make a horribly incorrect decision, thereby putting the system into danger. And what is really scary about this failure mode, even though it seems to be quite rare, is that it is a silent failure, which is to say, when it does fail, we don't really know that it fails. Rather, we need the human operator to be able to step in and say, that doesn't make any sense given the data that we see on the board. This has to be wrong. Let's run the simulation again. And we can see that whereas humans have the deep understanding, intuition to make this judgment call, it is a hard task for machine learning algorithms to make this assessment. And maybe this failure mode historically was seen as unlikely, quite rare, but over work that I've done with my collaborators over the past few years, we've constructed many cases in which even very simple networks with just 1 or 2 buses, we can construct cases in which it has both a global minimum which corresponds to the correct system state and a local minimum that is plausible but ultimately incorrect and would lead us to make an incorrect decision. And both estimates are plausible. A further concern is maybe an attacker or a hacker adversary could use this mechanism to induce us into seeing something that they want us to see that's not actually happening on the grid. So this is something that's of a concern, certainly from a human operator standpoint, but most of all, if we want to ever have an algorithm take the wheel, that we need to fully resolve this potential failure mode. And we know already, even with human operators, when the state estimator becomes faulty, it can cause serious issues. In 2003, after the blackout, it was realized that the state estimator was in fact faulty for most of the lead up to the fault. And that's to say, for the hour or so before the fault, the system operator was driving blind, that they didn't actually know what was going on. And after this event occurred, there was a post-mortem in which there was an analysis as to exactly what happened. And what they discovered was the grid, the angles between just one particular line between these 2 buses, a bus in Cleveland and a bus in Western Michigan. It started off at an angle of something like 15 degrees, 15 degrees. And over the course of an hour, it slowly diverged to 30 degrees. And in the report, they discuss how this is something that a human operator, if alerted to this, would certainly be able to catch and save the grid, but because the state estimator was just altogether offline and nobody had any idea, and the last 3 minutes, the angle quickly diverged from 30 degrees to 45 degrees to 50 degrees to essentially snapping the rod, and then that caused a cascading failure, which then took out 100 million people. So in this talk, what I want to talk about is this connection to phase synchronization. And I want to upfront tell you what the benefits of this connection is, the benefits are. The first benefit is, instead of trying to do this iterative refinement, starting from an initial guess that might be good or bad, what we do is we look at the problem and we're able to somehow develop a provably good estimation from the get-go. Just from the structure of the problem, we can come in here and immediately develop a solution that doesn't completely solve the problem. When you have noise, it doesn't completely solve it, but it's provably good as a solution to the problem. And we think in many cases, you could just take the solution and use that as an estimation. But of course, we might be concerned that this is not the best possible, and we could do iterative refinement using this as a high quality initial guess. And moreover, once we've refined it, we can then provide a certificate of correctness from Lagrange duality. In fact, it's yet another eigenvalue computation that then we prove that the converged iterate is in fact the best possible, and therefore within the realms of this particular estimation problem, this mathematical problem, we have achieved the best possible solution. And so it certifies the quality of the solution. In many cases, within one iteration of refinement, we're able to get the provably good estimation from this without needing to do any sort of starting from a faraway solution and iterating. Okay, so that is the benefit that we stand to gain by making this connection. So now I want to move to the second part of my talk, which is to explain exactly what I mean when I say phase synchronization, and to provide a little bit of technical background for how we're able to utilize this connection to actually solve the problem. So this second part of the talk will be a little bit more technical, but finally we'll conclude with some higher level discussions on future work, which should hopefully be a little bit more accessible. So to begin, I want to talk about what synchronization is, and this is a very accessible, very intuitive idea that when you put metronomes of, for example, different frequencies and different phases onto a balancing beam, that the coupling introduced by the balancing causes these metronomes to eventually agree in their phases. And not only in their phases, but also in their frequencies. Even though they could have started off with different frequencies, they eventually decide to exactly coincide in the frequency of oscillation. And this seems like a very peculiar and very whimsical example, but in fact it appears widely both in nature and in human interactions. One very prominent example in nature is the flashing of fireflies, that fireflies tend to want to flash with a frequency that somehow is similar to their neighbors. So they flash at a frequency, but they're able to see their neighbors, and this circle is showing the neighboring fireflies of a particular firefly. And just by seeing the neighboring fireflies flash, it induces them to either speed up or slow down in just the right way, such that globally, when we examine all the fireflies, they flash at roughly the same frequency and the same phase. So this is not limited to just animals. In fact, humans have famously seen several examples of this happen in real life. This is a video of the Millennium Bridge in London when it first opened in the year 2000. It was on a day with relatively high wind, and the bridge started to sway. And what is very interesting, as the bridge started to sway, the people who were walking across the bridge had no incentives to agree on their frequency, started to synchronize with the oscillation of the bridge. And you can imagine, as they synchronized the oscillation of the bridge, it made the bridge oscillate even more. And we also see cases where you go to a concert and people are clapping, and at some point the people start clapping at the same frequency just spontaneously without being induced. That by hearing other people's clapping, they eventually coincide, and you can see now that they start to coincide in the frequency of clapping. So these are phenomena that are widely seen throughout the world. This is why it's such an interesting thing, and this is why there's been so much work trying to understand it, both from a mathematical perspective and from a nonlinear physics perspective. And one of the most fundamental questions to ask regarding this problem is just, under what conditions does it occur? It doesn't always occur. So when it does occur, it's very interesting. Under what conditions does spontaneous synchronization occur? And the next question is, suppose that it does occur, what is the configuration that it converges towards? And it's a very non-trivial connection, but eventually it turns out the solution to both questions ends up being something that is remarkably similar to state estimation. And that's the following problem here, okay? So suppose I have 4 angles, and they're just points on a circle, so to speak, right? 4 angles, and I can measure the relative angle between them, so the offset of angles. So I can say that the angle from the first angle, theta 1 to theta 2, is 10 degrees. The angle from theta 2 to theta 3 is 10 degrees. 3 to 4 is 10 degrees. And the angle around from theta 4 to theta 1 is 340 degrees. So you can see from this here, if you just do a bit of math, you see these angles are not consistent. But then we ask the question, what's the most consistent set of angles that's going to resolve these numbers to the best of their abilities? And that turns out to be the solution to both questions here. And so this question of asking, I have a bunch of angles that I don't know, but I know the pairwise differences, the pairwise offsets, and I measure certain pairs. I don't necessarily measure all pairs, and I want to find the most consistent angles. You see, this is the problem, and you can also see now it ties very, very closely to power system state estimation. I have a grid here with 4 buses, and I have an angle for each bus. And what I'm going to do is I'm going to measure the angle differences, and I want to estimate the best angles possible. So you can see how the solution methods for this problem could be naively applied to power system state estimation. So let's talk about how this problem is actually solved from the mathematical perspective. So this is yet another non-convex optimization problem. The preferred way to do it is not to talk about angles, because we have this issue of circling around. And we need to somehow understand that 340 degrees is the same thing as minus 20 degrees. And that is not something that's very easy to work with on a linear line. So instead, what they do is they define points on a circle. And here, it becomes very clear. So I have 10 degrees, 10 degrees, and 340 degrees. And I want to find points on a circle that base this relationship here, in which I multiply by what essentially a rotation, I get the next angle, next point on the circle here. So this particular optimization, the important thing is it doesn't have this module or arithmetic going around the circle, and so you can just solve it as an estimation problem, in which instead of solving this as equality, we ask it to be as close as possible to equality as sum of least squares among all of the pairs being measured, and I restrict all the points to lie on the circle, of course. And this problem turns out is profoundly linked to spontaneous synchronization. This is, in fact, the underlying energy that is being minimized by the dynamical system. And the Euler-Lagrange equations that come out of this particular optimization turn out to be exactly the oscillation pattern of the synchronizing oscillators. But for us, it's also just kind of a very simple thing of, we just want to solve this optimization problem, and if we can solve this optimization problem, we can solve state estimation. So here I want to introduce this eigenvector technique that was first introduced in 2011 by Amit Singer, and it's based on a very, very simple insight, which is that if every single one of these numbers here is constrained to have a magnitude of equal to 1, then I can just add up all of their magnitudes, and then I notice that the sum of all of their magnitudes squared is going to be equal to n, because each individual one is equal to 1, and I add up n of them, and it's going to be equal to n. And that this particular problem, very non-obviously, this took me some steering to fully understand, but he claimed that this is equivalent to an eigenvalue calculation. And this becomes more clear if we can recognize that this particular operation here is in fact the norm of a certain matrix times a vector. And if we believe that, then we can look at this and see that this is indeed just some kind of eigenvalue problem. Now, the important thing is eigenvalue problems are well established. You can just have standard toolboxes and you can go and you can try and solve them. And moreover, the optimal solution is an eigenvector, is the bottom eigenvector, which then we can use as the initial guess for this estimation problem, for this here, the global optimization problem. And so that is our initial estimation. And the second thing is that this relaxation that provides a lower bound simultaneously provides a certificate of correctness. And that's to say, if we plug the eigenvector to this problem and it gets a value, an upper bound, very, very close to the lower bound, then we have not only solved the problem, but we have provably solved the problem. So this technique by Singer, it attacks this problem of estimating points on a circle given angles between them by the following. So it computes an eigenvector to this particular problem, which is not super obvious as an eigenvector, but there exists a recipe that's going to spell this out as an eigenvector of a certain matrix, and then we're going to just compute the eigenvector somehow. And once we computed the eigenvector, we're just going to put it back onto the circle and then that's going to get us the estimation for the points in the circle. And moreover, we're going to use the associated eigenvalue to provide a lower bound to prove that whatever we just estimated is correct. And so this has been studied. It actually took 10 years for there to be a coherent theory that guarantees that, in fact, this thing here is somehow provably good. And what I mean by provably good here is if all the angles are perfectly consistent, instead of having 10 degrees, 10 degrees, 10 degrees, and then 340 degrees, which is minus 20, then we had 10, 10, 10, and minus 30, then this procedure will immediately solve the problem in one go. And as that inconsistency grows, as there becomes more noise to the measurements, that the measurements are slightly off correct, that the estimation error grows proportionally. And if the grid, if the connections are very well connected somehow, then the estimation would be really good. So in one sentence, what this theorem is trying to say is that if the pairwise measurements are near consistent, that they're not too noisy, and that somehow the underlying graph is somehow connected, then you just solve this and you get a one-shot estimation of the points in the circle. Let's talk about what this means for the grid. Okay, so here I'm showing a picture of the 39 bus IEEE test system. So what we want to do, let's just imagine, let's just assume without loss of generality that one, we know all the magnitudes, and two is we know that all the magnitudes are equal to one. So they could be any value, but the important part is that we know all the magnitudes. And so our only task is to estimate the angles of all the voltages. And here we realize that the branch currents, the branch power flow allows us to, in fact, estimate the angle differences through that formula that I presented at the start. So from knowing the flow between the different buses here, which are often measured, not always, but often measured, we would be able to compute angle differences that then we can just shove into this algorithm, and it's going to provide us a state estimation. And so this would just solve our problem in one go. And it's provably good. We can opt to refine it if we choose, or we can just use it, take it, and use this as a state estimation. Now, what is the problem is what I just said before, which is what if the branch flows are not measured, right? And your branch flows are sort of peculiar. It's more likely that we're going to measure the bus injection. So for example, the amount of power generated by this generator here, the power generated by this generator, or the power taken out by the loads at each one of the buses. So that is more likely the value that's being measured. And the problem is that we cannot disentangle the power flow out of a bus with, which side did it come from very, very easily. And doing this is sort of half the problem already. And so we can't really work backwards to figure out the branch flows from the nodal, the bus flows. So we have how much power is being generated, how much power is being consumed, but we don't know how that power is flowing through the system by and large. And we still want to be able to estimate the angles given this piece of missing information. So how we do that is this paper that we propose here. And so once again, we're going to assume without loss of generality that all of the magnitudes are equal to one. And the critical insight for this paper is in fact this estimation problem of nodal power, right, the bus power. This particular problem here can be exactly reformulated into this form here. Okay? And what is important about this form is once you write it into this form, you can apply the same insights that I just presented to you that Emmett Singer introduced in 2011. And going through this, we end up with a solution once again as an eigenvalue problem. And just as before, what we can do is we can take the optimal eigenvector and use that as a state estimation. And we also have a guarantee of correctness from the spectral relaxation. So the key leap is this, seeing that this estimation problem is in fact exactly something that is of the correct form that we can apply the same technique without this being exactly the same. It is in fact quite different. So with that in mind, we have something that very much parallels the solution approach from this prior work, which is to go in here. I want to estimate all of the voltage phases I know all the magnitudes are equal to 1. I don't know the angles, but I do know, let's just say, all of the bus injections, so all of the generation and loads at every single one of the buses. Then what I can do is I can compute the eigenvectors for this particular thing here. Turns out to be a sparse eigenvector problem. And once I compute the eigenvectors, I also do this rounding in which I adjust the magnitude until it matches my measurements, which here is just equal to 1. And then I use the eigenvalue to certify the correctness of this. So I also have a theory that's very, very recent. This is not yet released, that this enjoys the same sorts of properties. I just want to spell it out for you in English. What it says is, if your bus measurements are relatively consistent, so they're not too noisy, then this will just get you a one-shot recovery, assuming that your underlying network is connected. So it's a very similar style of guarantee as what we saw before. If I have a connected grid, and if my measurements of the bus powers are relatively good, then I can just solve this problem in one go without ever iterating. It just goes in here and it solves the problem. And I just want to mention here, because I'm going to just stop the technical part right here, that there is in fact a generalization to mixed bus and branch and PMU measurements. We can also extend this to the case in which only some of the voltage magnitudes are known and not others. So this is a lot more technical stuff, and I don't have the time to really go through in detail, but I do refer you to the paper if you're interested in how these extensions work. But they all rely on some of these crucial ideas that I just presented. And now I want to shift gears to actually talking about the results when we apply this technique. So here we apply this technique to the European electric grid model from PGASE with 13,000 bus and 20,000 branches. It has 4,000 generators. And here I'm showing is the estimation problem in which I throw out all of the possible branch measurements and only make the estimation with bus measurements. In fact, I could even throw out some of the bus measurements, but just to make this comparison fair, I chose to just keep all of them so that we don't have to debate as to which measurement I deleted, and maybe we are cooking the results. So I've just included all of the bus PQ measurements, but I got rid of all the branch measurements. And what we see here is that with a 1% noise, that this method is so good that it gets the estimation within 0.4 degrees, that we could just use this out of the box without any refinement, without any further consideration, right? But if we do choose to refine, it does make it even more accurate, and then we now get it down to about 0.1 degree error with just a single iteration. And after that, further iterations, which are shown in red here with the red circle, they don't really do anything. And we just plot it here to show that beyond one iteration is basically as good as you're going to get. Now, with a larger amount of error, let's say 10% error, right, 10 per unit, that's quite a lot of error. And we're saying 10% error across every single bus, right? So there's quite a lot of error. Just by applying this eigenvector estimation, we get 4 degrees of error. 4 degrees is pretty large, so you do need to refine it. And within one iteration, we get that down to, once again, below 1 degree. And further refinement doesn't really improve it here, okay? In this same scenario, what we can further do is certify the optimality. So what we do see here is this, okay, so what we're plotting here is the mismatch, the cost function that we saw before, the mismatch to getting an equality on the measurements and the estimation. So we said that the measurements are inconsistent, so we can't get equality. This is how far away from equality it is. So we see that the solid line is plotting, how far away the particular estimation that we have is to establishing equality, and the dotted lines are showing the certified lower bounds. So we see that the initial certification is pretty loose. That doesn't get you a very good guarantee. It's just saying that the mismatch could be, 10 to the minus 3, so 0.1%, or it could be, wow, like 100%. So that's pretty bad. But within one iteration, it becomes almost exactly tight, up to 10% noise, right? Up to 0.1 per unit noise. It certifies the correctness up to 99.9%. with just one iteration, and we can make this guarantee. And these are only PQ measurements as well, right? Once again, we're not looking at the PQ bus measurements. We're not looking at the branch measurements. If we choose to include all the measurements, this particular scenario ends up with 100,000 measurements. But this thing here of computing an eigenvector can be very, very cheap if we utilize the right approach based on sparse matrix ideas. And in using sparse matrix ideas, we see that we get this provably good estimation from the eigenvector of the sparse matrix in less than half a second for this 13,000 bus model that's supposed to represent the entire continental Western Europe. And that certification then takes a quarter of a second. And from half a second, quarter of a second, we get an estimation that is provably good and certified to be good. So that is what phase synchronization brings to the table here. By using this eigenvector, we're able to make significant progress on the state estimation problem. So now I want to conclude the talk by discussing what the remaining questions are and how much further we still need to go to really achieve grid perception. One burning question I'm sure many in the audience are thinking is that, well, a huge problem for existing state estimation algorithms is not just being able to estimate against some amount of noise, but rather being resilient to bad measurements here. So, for example, one of your measurements, one of your power flow measurements, the current transformer could be put in the wrong direction, and so inject 180 degrees phase error, and all your measurements that particular measurement is wildly off. Can you still make an estimation given some bad measurements? Maybe maybe there's a topological change, and the topological change will induce very bad measurement. So we've done some initial experiments. I would say in this particular paper, our primary focus is just simply introducing this very novel connection and this ability to apply this technique at all. But in our private experiments, we do see that it's extremely resilient to outliers. So I think this is important follow-up work that we're currently pursuing right now. And this is not surprising because Amit Singh's original paper, this was in the abstract of his paper. He said he estimated 400 angles from about 100,000 measurements, in which 90% of the 100,000 measurements were completely wrong. They were completely outliers. And so we're not talking about one or two bad measurements. We're talking about almost all of the measurements being bad. And yet, he is able to estimate. So we think that this technique is very, very special and is able to somehow be much, much better than sort of the prior techniques for computing this estimation. And for me, it was really, really exciting, this idea of, okay, bad measurements, by and large, they're put in due to sort of an accident, right? That those measurements put in the wrong way. But now we're kind of worried that if we're going into algorithmic future, that maybe an adversary can go in and purposely plant bad measurements to induce us to do something. So something that I'm really interested in is trying to answer this question of, can we resist bad measurements that have been engineered to be bad, that the adversarial bad measurements, can we still get the correct read of what the system is doing? So in the perception layer, if I were to put stickers on the stop sign, will I get confused, or am I able to resist and see it still as a stop sign and not a 45 miles per hour limit? I would say in this work, so far what we really have addressed is some of these ideas with sensing and estimation. We turn the stream of zeros and ones into voltage phases, the magnitudes and the angles. But what's still missing is trying to understand these magnitudes and angles. How close is the system to collapsing? Now we know these values. What are the problematic areas? So this seems to be mostly an open area that has seen too much work. And so I think there's a huge opportunity for us researchers to really focus and ask these questions rather than using AI to solve the problem, which by and large could be achieved. The question of can we bridge the perception gap, to me, is the most important gap that needs to be bridged before we can realistically see applications of AI on the electric grid. And of course, the problem solving part is still important. Right? So we still need to ask, these techniques of using phase synchronization. We only talked about the context of solving the perception problems, but can we use it to also solve the actual problem of operating the grid? Dispatching generation, scheduling generation ahead of time, planning outages, planning loads. So these problems could potentially also be attacked using phase synchronization. So with that, I'd like to conclude my talk. At the start of the talk, we saw that I made a case that for AI, for cyber physical systems, the most important bottleneck is in fact the perception layer before we can really even think about applying AI to the actual solution. And the current approach is susceptible to failure, and we're really worried about the silent failure that induces us to do something wrong. In this paper, we've introduced this connection with phase synchronization, showing that it allows us to compute provably good initializations and certify the correctness. But this question of resilience, right? Resilience to bad measurements, but adversarially bad measurements, is a very important future work that we need to do. And also trying to feed this into a next layer to help us understand exactly what's going on. How far are we to the edge of the cliff from a semantic understanding perspective? And can we apply these techniques to the operations aspect of the electric grid? So with that, I thank you for your attention. I'll be happy to take questions. Thank you.
Thank you, Richard. You finished on the dot, 50 past the hour, so very good. So, I mean, we are going to address now questions from the audience, but as there are none in the chat box yet, I can start, I guess. So you talk a lot about phase synchronization, and are these results somehow related to all the literature in Kuramoto models?
Absolutely, absolutely. That is in fact the connection that I didn't want to go too deep. I realized that it was very technical in the end. But in fact, this connection here that I said, this connection here is in fact the connection to Kuramoto oscillators. And this energy, which I just said is the energy of the system, is in fact the energy function of the homogeneous Kuramoto oscillator.
Okay, very good. So then when effectively, I mean, in your when you're setting up the problem, what you're trying to do is come up with the fixed point of the Kuramoto dynamics.
That's exactly correct.
That's what you are doing, and you're assuming you have imperfect information, so you may not all the angle differences, so you cannot really set up the problem to solve all of them, etc. Right?
The imperfect information is a critical part of this, right? Without the imperfect information, it becomes trivial, because if all your oscillators already start off at the same frequency, then it's unsurprisingly they end up at the same frequency in the same phase, but that when they start off with different frequencies and different phases, that they somehow converge. So that requires you to set up the problem such that there's inconsistency in the data.
Right, but I mean that's I mean even if you have like all the injections, for example, I mean you could still compute all the angles by inverting the relation, right? I mean it's non-linear, but technical. It's like inverting, you know, I equal to YV. In this case is P. There is some non-linear relation between the angle differences and the injections. Nevertheless, that's I understand that now. Now, one other thing that I wanted to ask before I let other people chime in is in all this, are you assuming the network is lossless, which is the, you know, when you write down the Kuramoto dynamics and you try to link it to a power flow model, that's the underlying assumption. I saw there was the Y-bus matrix somewhere in the formulation. Are you assuming lossless?
Just any Y-bus, any Y-bus. We don't need to make any assumptions on the Y-bus. Okay. Other than that, it needs to be connected, obviously. It needs to have an underlying graph. And the graph needs to be connected, of course. Yeah.
All right. Sounds great. I'm going to stop there, and I'm going to ask a few other questions from the Q&A. So, great presentation. Can you talk about the resolution of the estimator?
Yeah. So I want to make two comments. One is that, okay, so in regarding the resolution, you know, so the initial estimator has some amount of error, and that is its resolution. And so here we see that with 1% noise, you get 0.4 degrees of error. So that resolution is pretty good. And you know, even with 10%, so the resolution is about 4 degrees here. That's not good, and we need to do one iteration of refinement to get it down below 1 degree, in which it becomes good again. However, I also need to point out that like at this point here with 10% noise, the resolution of about 1 degree is fundamental to the problem. And that's to say, information theoretically, you can't really get better than that. Indeed, with further iterations, now here I've blocked out my key here, my legend, but with 5 iterations, it doesn't change the error. The error doesn't go down because information theoretically, when you add the noise, it destroys the resolution. And so just fundamentally, you can't get it more precise than in this case here, about 1 degree. But you see that, information theoretically, it's about 1 degree, and then we get to 4 degrees from the get-go, and then with 1 iteration, we get it down to 1 degree. Now, finally, that ratio between 1% and 0.4, this does depend on how connected your network is. So if your network is almost disconnected, then you can imagine that it's just fundamentally impossible to estimate some of the angles, and that also is kind of information theoretic bound. So then we can make some estimation, but then the estimation won't be good. But then with however much iterations we make, it still wouldn't be that good. It's just fundamentally there's some lost information. So within the setting of the amount of information in the problem, we're able to be half a order of magnitude, which then gets refined down to the exact value.
Okay. Another question here, technical question is, what are typical bus measurement errors? Are they in the order of 1 to 10% or less on average?
I think it really depends on the bus. Like obviously, if you have a generator bus that, you have all these protection schemes, then the error is going to be very, very low. Whereas now if you say, hey, I want to apply this to a distribution network, then historically the error is extremely large, right? Because it's not very well measured. So that is something of a concern. One could argue that the badly measured buses could be like bad measurements. So we're working with potentially as small as less than 1% error to as large as say 30% error. But I would say on the transmission network, I think 5% is a reasonable number.
Mm-hmm. There's another question about the measurement observability in the grids to solve this problem. I think the person asking might be asking about the coverage, measurement coverage. I mean, how many measurements? That's my guess. What this observability question really means. I mean,
yeah. So observability is an excellent question. In fact, that is intimately tied to things like how connected the grid is. In fact, I say connectivity, but really I'm saying observability, and it is in fact the connectivity that drives the observability. So observability is the fundamental underlying thing that drives whether this thing can work. But that also determines, that's the information theoretic limit as well as to how well you can make the estimation. So absolutely, we're not able to just overcome the lack of observability when there's no new information being introduced. But rather, we can make use of that information in a way that doesn't get stuck, that gets to some optimal value. But in fact, trying to boost observability is always going to be a separate problem to be solved by the hardware experts here.
All right, I think we have great time for one last question. Is how frequent you can run this estimator? I guess how long does it take for it to converge before you can run the next one?
Yeah, so the great thing is that there's no convergence, right? You just run it and then boom,
Yes,
it computes
yes.
the eigenvector.
I mean, solving it, yeah, it's one shot.
Yeah, so it's one shot and then you get this value. And here, 13,000 buses, we took like half a second. I would not claim that our implementations by any means even close to being commercially viable, right? It's just, written in a rush. And so I expect the number to be basically negligible.
Great. All right, so we are close to 1 p.m. We are going to stop here with the questions. If your question is not answered, you might send an email to Richard. I would like to thank you all for joining us today. If you please, can you respond to the one question poll that is gonna pop up on your screen right now? And I just want to close by announcing that the next webinar will be on March 5th, and the speaker will be Lina Roll from University of Wisconsin. So thanks again for joining us today, and have a great rest of your day. Thank you.
Thank you.
Thank you, Richard. That was a great webinar.
Thank you. All right. See you
I'll,
later. Bye-bye.
okay, see you. I'll send a follow-up email with your webinar stats,
Okay.
probably by end of the day.
Okay, great. Thank you.
Thanks.